So the blue family is a family of is a family of triangles in so-called Brocard porism. Brocard porism is a family of triangles inscribed in a circle and circumscribing the so-called Brocard in ellipse, this brown thing here, where the two foci of the caustic happen to be the stationary Brocard points of this family of triangles. Okay, now what I'm showing up here are conservations that have been shown elsewhere, that this family conserves the sum of cotangents of its internal angles and the sum of its inverse square side lengths. Okay, so you can see here the numbers. Now what we're also showing in green is the tangential triangles to this family, namely the green family whose sidelines are tangents to the circumcircle of the Brocard triangles, of the Brocard porism triangles, at the vertices. So you get these green triangles. Now, what we noticed here recently is that this family conserves the sum of half-angle tangents. These SDs equals 0 here just means that the standard deviation of these values here is basically 0 over the family. Okay, so you can ignore this. This is just a double check. So the other thing that you notice is that that sum is equal to the sum of cotangents for this particular family here of n equals 3. Okay, so we're getting the same value for this invariant half tangent sum on the green triangles, the polars to the brocards, that we're getting to the sum of cotangents for the brocards themselves. So that's kind of interesting. If I change the eccentricity of my brocard in ellipse, I change the sum of cotangents, but these two values are still the same. What's being conserved by the blues is equal to what's being conserved by the greens numerically. Okay. Now let's try the same family where I'm going to try an n equals 4 in here. Here's n equals 4. Let's make this be more visible. Now when you make that polygon have more than 3 sides, these are known as harmonic polygons, and I'm going to leave a link in the description for a paper where we study these. Okay, so the n equals 3 is a special case. Now you can see here that for n equals 4, the sum of cotangents for the blues is identically 0, and this is always the case. Whatever the eccentricity of this harmonic caustic or Brocard caustic is in the, if you want to abuse that term. You can see here that the sum of cotangents for n equals 4 is always 0. Now you can see here that despite that, the outer, the green one, the polar, or if you want tangential, the n equals 3 case, is also conserving the sum of half tangents, but now the values are different. Recall that for n equals 3, they were the same, okay? Let me make that n equals 3 come back here to the screen. So for n equals 3, they were the same. What we're seeing is that for n equals 4, they are not the same. You got 0 for the sum of cotangents, and then you got some finite value for the sum of half tangents. How about n equals 5? Let's make this guy become more visible. And I think I can increase the number of samples here. Is that how it goes? So let me hope that I don't do anything wrong here. Yeah, so that's n equals 5. For some reason, my samples, yeah, there you go. So if I just move n equals 5 here, let's try to make this thing be a bit more visible. Like, yeah, it doesn't matter, right? So this is an n equals 5 family of harmonic polygons. Yeah, let's go back this way, maybe like that. Yeah, and then let's just animate that. Now let's look at what's happening. The blue n equals 5 harmonics are still conserving, and you can see here that now the sum of cotangents is a negative number. For n equals 3 it was positive, for n equals 4 it was equal to 0, and now for n greater than 4, this sum of cotangents becomes negative. The sum of inverse square side lengths is still being conserved by the blues, and now you're getting, again, a different number here. Different number, right? We wonder if this number and that one are related somehow by a constant, right? If I multiply this guy by 4, you get roughly 10 and then 4. Yeah, it doesn't look like it's exactly a constant, but this is just showing that for n equals 5, the green family also conserves the sum of half tangents. How about n equals 6? Can I even do that? Let's see that. Let me change, yeah. Let me change the number of samples to maybe 5, like that. Yeah, so you can see here again, we're getting a conservation of a negative sum of cotangents for the blue family. The sum of inverse square lengths is being conserved for the blue family, and then you got this conservation. Again, it looks like, you know, this is 3 times something. It could be that there's like a simple factor here. Let's look at n equals 7 now. Can I play around with this eccentricity? Yes, I can. Again, I'm getting a sum of cotangents that is negative for the blues, a sum of inverse square side lengths, which is constant, and then here I have a sum of half tangents for the greens. So it looks like this conservation is working for all n. All right, I'll see you on the next video.